We present light sampling field and BRDF representation for physically based neural rendering. In this work, we propose a physically based neural rendering pipeline allows for realistic rendering of complex objects, such as translucent and organic materials. These materials typically possess a multilayer structure, which makes the light transport more intricate and challenging due to subsurface scattering and other complex interactions. For example, when considering human skin, the incoming radiance can be partially reflected directly at the outermost oil layer, resulting in both specular and diffuse reflections. Some of the incoming light may penetrate into the epidermis layer after reflection. Once inside, the light may interact with particles and bounce around before either penetrating deeper into dermis layer or exiting the skin from a different location. We start from the physically based rendering equation, where the outgoing radiance at a given point being determined by the interaction between the incoming radiance and the material. We further developed our rendering equation to model lighting and the light transport within each layer. Our approach begins with the disentanglement of the surface specular reflectance from the direct light term. This term specifically captures the common reflections that occur at the topmost layer of a material. In addition, objects with coarse surfaces exhibit diffuse reflection on their surfaces. This behavior is described by the second term in our approach. Furthermore, we model the subsurface light transport within the material by subsurface scattering reflectance with the indirect light term. By employing this decomposition, we can effectively replicate the intricate light propagation through a learnable material model and lighting model. The material model comprises of three key components: surface specular reflectance, surface diffuse reflectance, and subsurface scattering. Our material network takes sample position and view direction as inputs. It generates outputs for specular strength and scattering in our canonical space. When combined with pixel alignment albedo, we achieve a comprehensive material representation. Our lighting model consists of both direct illumination and indirect illumination components. In the case of direct illumination, we propose importance light sampling to automatically mitigate extreme values and facilitates precise shading through adaptive sampling. For indirect illumination, we introduce a light sampling field that accounts for reflections from surrounding objects. This approach is motivated by the visible spatial variability of local indirect illumination under fixed global lighting. To implement this, we propose a light sampling field network to construct the local indirect illumination incorporating the reflections from the environment. The light sampling field network takes sample position, view direction, and direct light embedding as input and generates a learned first order spherical harmonic field that represents the local indirect radiance. To integrate all the components, we propose an end-to-end physically based neural rendering pipeline. This pipeline takes as input a coarse geometry, an albedo map, a normal map in UV space, and an arbitrary HDRI. As an initial step, our pipeline performs recasting to generate resamples from scene geometry. The samples are then embedded along with the view direction into the canonical radiance field. These embeddings are utilized as input for the material network, which follows the architecture that we previously described. In parallel, our pipeline employs importance sampling from the input HDRI. We further use a downsampled version of the HDRI that comes with the importance sampling to generate light embeddings. These light embeddings, together with the other encodings, are incorporated into the light sampling field network. We map these values along with the input textures to the canonical radiance field and conduct volume light transport in the field, as well as the light transport in the multilayer materials. Our proposed rendering equation further composes each component and outputs for final renderings. Here we show some results from our rendering pipeline. For any target to be rendered, given the rendering asset and the target illumination, our pipeline can render a photorealistic image queried from any viewpoint. We also show inverse rendering, where we have an extra module for density field prediction. We conduct a comparison between our rendering results and those of Maya, an industrial-level rendering engine. While preserving the same high-fidelity rendering quality, our method demonstrated an impressive 48 times increase in faster rendering speed. Our rendering pipeline also supports super high-resolution rendering with pore-level detail. We show zoom-in views of a 4K resolution rendering example. Moreover, with the pre-trained light sampling field network and the material network, our rendering pipeline can support reliable dynamic sequence from multi-view. We additionally show direct diffuse and direct specular from light probe as an intermediate result. Thanks for listening. Please check out our paper for more impressive results.